So here's the next question about stars. Can we actually figure out how hot those stars are, those points of light? Well, in order to answer this question, we need to remember that every object emits thermal radiation. Remember that? We call that black body. Right? And that thermal radiation is a spectrum that depends on its temperature. Remember how it looks like this? Intensity. If we are to measure the intensity as a function of wavelength, we always get something like that with a peak. Maximum intensity, and that corresponds to a certain wavelength. And once we identify what that is, we can convert that using Wien's law into a temperature. So basically, this is what happens. They have different colors. These different stars, different objects, if you want, at different temperatures, have different colors. And we have here 3 examples. And we have a hot star, medium hot, if you want, and kind of a cold star, right? So only 3,000 and then about 6,000 Kelvin and then much hotter stars. So look at them. And for comparison, something really cold. Compared to stars. Of course, our soul better be warm. So that kind of, looks like that as well, right? There is emission outside this infrared range, but it's just tiny. So back to stars. You see how a cold star, right, in the visible, right, we're looking at it, is going to look like it's having a lot more red coming out of it than the blue. So it's going to look red, okay? The stars like the sun that have a temperature of around 6,000 Kelvin, it has, a peak at around the yellow greenish light, right? As we have learned in a previous chapter, there is, and you can see here the distribution of the intensity, right? So even if this is the max, there is comparatively highly intense light emitted in the blue and in the red. So altogether they make that white light that we get from the sun. Okay? And now let's look at this really hot one. It's pretty obvious that there is a lot more blue, that is intense blue than red. So this star is going to look blue in our eyes. Of course, if you were to observe it in UV, for example, right? Move here towards X-rays. Not really. It's really the hot stars they emit in the UV. Okay, so we have here infrared and then move to radio. Good to remember everything we learned in that chapter 5, isn't it? So, in order to measure the temperatures of the stars, all we want to do is figure out, just measuring intensity, and just as a reminder, this is power per unit area. So basically power per each meter square of that star, right? So here's how a cold star looks like, kind of red, and then this is the temperature of our sun, and this is, just measure the intensity of all wavelengths, and you're gonna find the peak. That's gonna be lambda max. That's the warmest star. Okay, so emits roughly equal amounts of light at all visible wavelengths, and so it's going to appear yellow-white-ish. And then compared to this really blue, right? So a lot more blue than red by comparison. So of course it's going to be appearing. So that's the infrared, this is the UV, and this is the visible. So that's all we do to measure temperatures, and it's pretty nice actually. We can get the temperature and therefore the color, and there is actually no need to know how far away stars are, because you know at every one of these wavelengths is going to be at the same distance, so you know it's not going to matter whether this is the intrinsic luminosity or just the brightness, right? So this is basically brightness per meter square. Nice. Measured a bunch of temperatures for hundreds of millions of stars, and the hottest ones we found out, they are going to be obviously the blue ones, tens of thousands of kelvins. Okay, that's how we measure temperature in absolute Kelvin. And the coolest stars, pretty cool, but not much cooler than a few thousands of kelvins. So maybe some of the reddest ones would be a good example. Okay, so just as a comparison, where the sun is somewhere in between. There are, as we will see, many more cold stars than hot ones. We're going to see about that later on. Okay, so if you remember, there are actually some other things that we learn by just pulling together, stretching light. So stretch light, right? The intensity we had is a function of wavelength, and so here would be the longest wavelength, so close to infrared, and here would be the shortest wavelength or the highest frequency or the highest energy, right? The blue, and this is the red, the reddest red, and this is where the maximum intensity would be. This is the spectrum of the sun. So this is where what the spectrum is, right? Intensity is a function of wavelength. You're stretching the light and look at every single wavelength, and you just cut that ribbon, you measure the intensity, and you put the cuts one under another, and we discover, remember, some features. We call those absorption lines, as they appear at certain wavelengths, right? So the intensity is much lower at certain wavelengths. And it turns out that for all of the stars, not just the sun, and we get, here's why. At certain temperatures, so we have cold here to really hot here, okay? And we know from experiments we run in the laboratory that the temperature is related to the level of ionization, or actually to what happens at the atomic level with the matter. For example, for cold systems, they're mostly in a solid state, so pretty much no motion, so very little motion of molecules, right? So cold means low kinetic energy. Okay, they're not moving very fast. They stay in their links and they form the solid, and then you go to higher temperatures. So by the way, there is again the same kind of typo we find again and again. So this is 100 Kelvin, this is 1,000, and then you go to tens of thousands of Kelvin, and then higher and higher temperatures. So here is basically 1,000,000 degree Kelvin, really hot. What's going to happen when we increase the temperature? Well, the molecules get dissociated, okay, so they're not going to stay together. You see the bonds are broken, and then here you start, so electrons are fast enough, or they have enough kinetic energy to break free from their atoms. And this is what we mean by ionization. So atoms become ions. So you're going to end up with free electrons like this, and then the ions, usually positively charged, left behind. And then if the temperature goes even higher, you know, maybe all of the electrons are going to break free, and you end up with a soup, a very hot soup of electrons, positrons, all kinds of charges. So not necessarily bound anymore into an atom, okay? So this is why at different temperatures you end up with different patterns in the absorption lines, right? So very few and lots of absorption lines here. And it turned out that the ones with very few absorption lines are the hottest, and those with lots of absorption lines are the coolest in temperature. They're all cool, they're stars in temperature, all right? And they have names, they're types, and the names are letters, and they show a sequence in temperature, right? So it goes like this: hottest, coldest. It goes from O, B, A, F, G, K, M, types from hottest to coldest. Okay, now this happen, right? There are some ways of remembering the spectral types. So we have O, B, A, F, G, K, M, right? That's the spectral series for stars. If you think about a star, you talk with an astronomer, you know, it's very useful to say, oh, that's an O type of star or a K type of star. For example, our own star, the Sun, also Alpha Centauri. Actually, it's a G type of star, and there are mnemonics that can help you remember these sequences. And here are some examples. Oh, be a fine girl or guy, kiss me, that's one. Or only boys accepting feminism get kissed meaningfully, or you can come with your own. So hey, I'm willing to give you some extra credit. 1 point if you turn in discussions for the page, just submit your own mnemonic. Okay, so go ahead and find one that's gonna help you remember the spectral type of stars. And a little bit of a history of how we came to put together this kind of sequence. So it was, I think, in the 1912, 1913, or say 1910 and on. It was at Harvard College, and Edward Pickering was the director. Here in a picture with his assistants or calculators, the human calculators, and they looked a few tens of stellar spectra, so basically a bunch of ribbons, and identified the absorption lines, and they say, okay, how are we going to kind of separate them, the way you're thinking, well, okay, there are different types of colors of the feathers of the ducks on a pond, right? Kind of a situation, because we want to learn more about them. And the first idea was, okay, why don't we do that by just counting the lines of the hydrogen absorption, and they started with type A and type B and type C and so on, and they arrived at M and so on. But then it was Annie Jump Cannon who realized, well, there is actually a much more natural sequence, and she realized that actually some of the letters O, P, whatever, some of the letters actually overlapped, and she came up with the O, B, A, F, J, K, M sequence. So it was one of the calculators who became very adept at figuring out the type by just looking at the pattern of the absorption features. But nobody actually knew why that sequence seemed that natural until Cecilia Payne-Kaposchnik, who was basically one of the first PhD thesis written in astronomy by a woman, and it turned out to be called unanimously, undoubtedly the most brilliant PhD thesis ever written in astronomy. So she was the one who figured out the physical understanding of the spectral classification, which is basically what we discussed so far. And she relied on insights of the new then quantum mechanics science. So she was the one that showed that the differences in the spectral lines from star to star merely reflected changes in the ionization levels of the emitting atoms. And it was not just that there are different atoms. She was the one that proved that stars, all of the stars that we see out there, are mostly hydrogen and helium. So this is very little of any other chemical element like carbon and nitrogen or oxygen. So it's mostly hydrogen, but the difference comes from the ionization levels. And so, for example, the O star, the hot ones, have really weak hydrogen lines because at their really high surface temperatures, nearly all of the hydrogen is ionized, and so there is no electron to jump between those energy levels once the atom comes by to produce that kind of, to be absorbed, right? And so there's now at the other end of the spectral index, the cool stars, the M stars, they're cool enough for some particularly stable molecules to actually form, and that explains their strong molecular absorption lines. So the cool type, there are many that form just at really low temperatures. So pretty neat. So she was the one to figure out why there is that sequence. And that's important. A sequence that shows a sequence in temperature, but it's also spectral type and also color. So very important.